Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. I'm Muhammad Ridwan bin Ghazali. My friends, Hazuraidah binti Ishaq and Professor Madya Dr. Muhammad Ashraf bin Ahmad. We are from University Malaysia Pahang. So today I will present on topic data-driven signal-based secretion rate of neuroendocrine PID control for TRMS systems. So this is my presentation outline. I will start with introduction and I will end with the conclusions. Okay, so for the twin rotor memo system or TRMS is replicates a helicopter-based dynamics. So this TRMS is a high non-linearity, high coupling effect, which is pitch and your angles. And then this TRMS required high accuracy controller and control systems. So currently the model-based control, which are derived from the first principle or system identifications. So this model-based controller difficult to apply due to the inaccuracy of simplified models. The unmodeled dynamic problems, huge gap between the control theory and the real applications. So now, what is the suitable controller methods? Okay, so we select data-driven control methods or model-free methods. So this why data-driven? This data-driven does not require any theoretical assumptions about the plant dynamics. Using input and output data to design the controllers, which is the control parameter. Okay, and then this data-driven control consists of two parts. The first is control structure and the data-driven tools. For the control structures, currently the PID controller is preferred due to the simplicity and the design and implementations. But however, in the complex and nonlinear system, PID may contribute the less control performance. Uh, some researchers propose the advanced PID, which is by using the bio-inspired controller, which is the neuroendocrine PID. So this neuroendocrine PID is generated from the nature combinations between the PID controller and neuroendocrines, and then the high efficiency and accuracy performance. However, the existing neuroendocrine PID control structures, the hormone secretion rate is a constant during the experiment time. So this constant hormone secretion is still insufficient in producing the better control accuracy performance due to unable to interact directly between the secretion rate and the control variable error. And unregulated control response of neuroendocrine also influence the cooperations between the neuroendocrines and PID controllers. So now, what is the suitable controllers for the RMS? So we select the sigmoid-based secretion rates, which is SBSR neuroendocrine PID controllers, for increasing the control accuracy of the existing neuroendocrine controller structure by varying the hormone secretion rate according to the change of error. So for the data driven, so we select the adaptive safe experimentation dynamics. So this ASED is optimizations by making random perturbations to its design parameter and holding the setting if they generate the best value of the objective functions. So this ASED is high accuracy in finding solutions, less computational time due to this ASED is a single agent based optimizations. And this ASED also memory based and independent gain sequence and adapt to the objective functions to avoid the premature convergence curve. Okay, for problem formulations of sigmoid-based secretion rate neuroendocrine PID, so this is the sigmoid-based secretion rate neuroendocrine PID controller for TRMS systems. So we have GS is a TRMS consists of main rotor and the tail rotor, so reflect to the horizontal angle and vertical angles of the TRMS. Okay, so this is the neuroendocrine PID controller consists of C11 and C22. C is the controller for PID controllers. So we have parameter KP11, KI11, KD11, and N11. And then for the neuroendocrines, so we have E11 and E22. So this is the equations of neuroendocrines. So we have Hill functions here. So this is Hill functions, and then we have the secretion rate here. Okay, and then this is the direction factor for the neuroendocrines. So in the sigmoid-based secretion rate, we modify from the fixed or the constant secretion rate into the variable, which is we use the sigmoid-based secretion rate. This is this is the sigmoid functions. So this is we're using this sigmoid functions. That's why we call our controller is sigmoid-based secretion rate neuroendocrine PID controller. Okay, and then all the parameter we need to tune by using the ASED algorithm or ASED optimization methods. So These algorithms, we use the tracking error and input controls here. So this is the error by using the ISE. I is integrating square errors. Okay, so this is the objective functions J, and then this is the weight multiplied with uh, the errors and the control inputs energy. So, based on the system in figure 2, so the parameter for sigma-based saturation rate are required in accordance to the measurement data obtained from U1, U2, Y1 and Y2 towards minimizing the objective functions J, K. Sini lah. Okay, now we move to data-driven tools, ASED algorithms. So, first we consider the optimization problem. So, to minimize the functions of F with the parameters P, so we need to find the P optimal lah. So, P optimal is our solutions. So, step 1, for generalizations, we determine the parameters for the range of the parameters and then the all parameter of ASED algorithm. And then we set for the first iterations K0 for design parameter P0 and the objective function F0, and then we update the value P bar based on the current value. Okay, now action selection and status update for step 1. So if FPK less than F bar, so we execute P bar equal to PK and F bar equal to FPK. If not, move the step 3. So step 3, we generate the random number RV1 and RV2. Then we update the PK plus 1 and FPK plus 1 by using the ASED updated law. So this is the ASED updated law. Okay. So, and then step 1 we return to step 2 and repeat until they reach the final iteration. So the stopping condition based on the K maximum lah. Okay, and then for the data-driven design methods, so this is the psi, J, K, P, J, I, K, D, and then etc. Okay, and then the total parameter is 20 for this TRMS for 2 input and 2 output systems. So we apply the algorithm scale to accelerate the explorations of P. So by using psi equal to 10 power of P, so J equal to 10 power of P lah. So the procedure data driven. So now we let the function here, and then we set the maximum iterations K max is determined, and then we implement the ASED algorithms. Okay, now we move to the simulation result. So we evaluate based on the objective functions, total norm error and total norm inputs. So this is the desired position that we set for tangent H. Okay. Okay, so this is the result. So we have the objective function or the objective curve here. So we have a convergent curve. So we set the iterations until 3000 iterations, and then this is the objective functions with the weight W1, W2, W3, and W4, and then the parameter here. So this is the initial value or the initial parameter result for the objective functions, and then this is the optimal result for the objective functions. Okay, for the graph, so we have the horizontal plane here, y1 response. So this is the y2 for vertical plane. So we have the reference here, the dot, and then the dash is the initial value, and then the solid black color is a ASED signals for horizontal plane and the vertical planes. So this is the numerical result for the objective function. So the mean is 2, 2, 2, and then the best for objective function, and then this is a total norm error, and this is the control input energy with this is the computational time. Okay, now for the conclusions. So we have conduct the simulations to demonstrate the promising result, the capability of sigma-based saturation rate towards tracking the error and control input energy for the twin rotor MIMO system for angle horizontal and vertical plane. And then we also obtain the statistical result for ASED based algorithms. And then so we find that the sigma-based saturation rate uh, have a superior control performance and also can tracking the error for horizontal plane and vertical planes. Okay, thank you.